This follows on perfectly from our last episode. Now, to quickly recap, the last episode was on injuries to the brain that happen at a specific moment. Today, as we alluded to last time, this is going to be about brain injuries that happen progressively over time, what are commonly called neurodegenerative diseases. So these are distinctly different from what we talked about last episode, but they do impact the same systems.
Yeah, I think a big word that differentiates them between acute brain injuries, it's another sort of an umbrella term within an umbrella term, but a big word that's going to be coming up is pathophysiology. So that means, obviously, physiology is the inner workings of our cells and our systems. That's just always going on in the background. And then it's the pathology of that physiology. So something going wrong. And each of these conditions that we're going to be talking about today have a distinct mechanism that they're causing to happen to the physiology in a atypical way. Very quickly to preface, there's the brain and the spinal cord, which make up the central nervous system, kind of the command center, and the main superhighway from the command center to the periphery. And then there's the peripheral nervous system, which is that periphery. So it's coming out from the spinal cord, out to the rest of the body, to your fingertips, to your toes, to your organs, so forth. And so I think we'll run through how things affect those different branches.
Yes, and so we're essentially going to try and use 4 main examples. So what we're going to talk about today is going to be Alzheimer's first, Parkinson's, multiple sclerosis, and then one called Charcot-Marie-Tooth disease at the end. So, Kenzo, there's lots of different kinds of neurodegenerative diseases. I think a really good place to start off with would be something like Alzheimer's.
Yep.
Because it's a good way, we'll start up in the brain and then we'll work our way down through the nervous system.
Yeah, perfect, I agree. So I guess to start with, a condition that affects particularly the brain itself, and that cerebrum that we talked about in the previous episode is Alzheimer's, like you said. And so it's a condition where it's associated with abnormal buildups of proteins in the brain. And so what proteins are, just to quickly explain, is within our cells, there's DNA, which is the code and the building blocks, the code of our body. And then when our body is dividing up its cells and just going about its daily machinery, it's transcribing or reading this code and turning it into proteins. That's what the DNA codes for, it's proteins. And those proteins are the building blocks that make up our cells and the machinery within. And what we see in Alzheimer's is that there's a mistranslation of this code where the proteins come out misfolded. And so usually proteins have a specific shape to do their particular function. You can think of them like they are literally building blocks of the cell. And so if one comes out a different shape, then it's not going to do its function the usual way. And so we see these 2 main buildups of proteins called amyloid plaques and tau tangles. And so don't worry about the names too much, but you'll probably hear them mentioned. And they're basically just buildups of these misfolded proteins. We'll allude to this later. We don't quite know yet whether those misfolded proteins are the underlying cause of the disease. We just know, or just a symptom. We just do know that they're highly associated with the disease process, and the more they build up, the more symptoms there are in Alzheimer's. And so that's the underlying pathophysiology behind Alzheimer's disease. Typically in the early stages, we do find that it affects the temporal lobe more so than the rest of the brain. And so we get a bit more of a build-up of these plaques in, say, areas of like the hippocampus, which are responsible for memory, which is why Alzheimer's is seen as a dementia disease. And so it causes problems with memory, which again is what the hippocampus is deeply responsible for. And as it starts to progress, those areas of build-ups of plaques start to spread to other lobes too. So we'll see it happening in the frontal lobe as well. So you'll have people will start to have personality changes as well as memory changes as it progresses. And then you'll start to see that maybe even manifest as motor deficits where they start to lose the ability to have voluntary movements, or things might be a bit different to how things were before. And as the disease progresses, not only are you getting these plaques spreading out through the brain more diffusely, you're also seeing that these plaque areas have neuro die-off as well. So neurons start to die off. Sometimes you get the brain a bit of a Swiss cheese look to it on scans, where it'll have shrunk, certain patches will have just died away. And so you're getting little patchy areas of diffuse damage across the brain and throughout, rather than like an acute brain injury where it's a specific region that's affected by itself.
Yeah. It sounds like, again, we're coming to this big factor of these types of neurodegenerative conditions is that over time they have the changes coming on.
Exactly. Yeah. So it starts off fairly mild,
Yeah.
and as time goes on, it can get progressively more and more severe, and it can be become a bit more diffuse and spread out through the nervous system. In this case of Alzheimer's, it's across the brain that it becomes pretty diffuse.
So just to summarize, it sounds like it starts off with more of that memory and the memory parts of the brain, just to simplify it. And as it spreads, it can start to impact other functions of the brain as well.
Yeah, more complicated memory, and then things like emotion, personality, and then even like voluntary functions as well.
Yeah, so motor symptoms towards the end.
Towards the end, yeah.
Yeah.
I don't believe it's every person. It is one of those things where a lot of these neurodegenerative conditions, because they're sort of are just underlying pathologies that sort of appear in different parts of the brain over time, it can be very different person to person. So that's going to be a running theme across at least quite a few of them, where you can have different manifestations of the same underlying pathology and have different symptoms because of that.
So I would like to talk about Parkinson's next, because it is a great example of a neurological condition having a very specific effect on one particular structure. So Parkinson's, now we're not going to cover the full scope of a deep dive into Parkinson's. We're just going to give a little overview here to try and help people understand what the changes over time, what changes over time are and how they differ between different types of conditions. So to give a rough idea of Parkinson's, there is deep in the brain, there is a structure called the basal ganglia. Within there is cells that produce dopamine. So these are stored within the substantia nigra.
I have a feeling a lot of our listeners will hear the word dopamine and they'll think, oh, that's the chemical responsible for happiness, isn't it?
Yes. Well, we've got news for you. Dopamine has so many functions in the body, and it ain't happiness. So on the contrary to what everyone seems to think, dopamine is not a happy molecule. It is a molecule of motivation. It's a neurotransmitter that helps to do lots of different things, but everyone seems to know the part that it does of motivation. They think that it's happiness. It's not. It's motivating you to do things that make you happy. Yeah. And it's really important for habit formation and lots of different things like that. But we're, again, not going to dive into that too much today.
Just to very quickly mention as well for audience at home, a neurotransmitter is a chemical so neurons carry electricity within themselves, but then to transmit that signal to the next neuron down the chain, it's a chemical that they use to communicate between neurons. But yes, it's one of the many in the brain.
So the substantia nigra starts to have a loss of these dopaminergic producing cells, and that starts to have an impact on the body. Now, the most obvious symptom that I think that we can help make this make sense is something called freezing of gait. So gait being walking, so freezing of walking. Now, this Parkinson's has a very specific effect, so it has a very obvious almost set of symptoms that go with it, which can be quite different to other neurological conditions. So I hope you can see my fingers down here. I'll bring them up a little bit higher onto my hand. So what the substantia nigra does for the basal ganglia is it produces the dopamine that helps the body start and stop movements. So if we start to lose this circuit that helps us, it's called an excitatory inhibitory way of getting actions to start and stop. I'm not going to dive into that, but essentially it's a way of getting things to start and finish. So a really obvious thing that happens in Parkinson's is starting off walking can be a really tricky thing to do. So while it seems like it's relatively straightforward, it's because the brain typically is struggling to get to hit the threshold of starting a movement pattern.
Despite the intention to move.
Yes.
The intention to walk might be happening in that motor cortex that we talked about last episode. but it's just not getting
Exactly.
through.
It just isn't getting through. So doesn't get the threshold to start the movement.
Mm.
So essentially, there can be almost like a very very tricky to get that first part of motion started from standing, which again can increase falls risk and has a whole bunch of other things associated to it.
Mm.
So if you think about it, once people start walking, typically they depending on how far along their condition is, can walk relatively well. But it's when they start to have to turn around or go through a doorway, something that just changes the pattern up a little bit, that can disrupt this circuit again of this, this having enough capacity to keep starting and stopping movements. They can stop the circuit and have freezing go on. So it looks like they want to step, but they just can't get that starting cycle, the start of the cycle going. So turning around gets really tricky. They can make walking look very shuffly, so much shorter steps to try and counteract some of the other impairments that come along. And again, this really helps to show a really specific pattern of what one change in the brain can have down the track on more of a global scale.
Yeah, I almost also, just to throw in one more quick analogy, but people who know about classical physics or they're into engineering or that kind of thing, it almost is like they have trouble overcoming a type of inertia, like movement inertia. So, this is terrible. I forgot the exact law of Newton's, but when an object in motion stays in motion, or if it's static, it's hard to start. Once started, it's hard to stop.
Yeah.
Hard to change direction. That's almost exactly what freezing ends up looking like.
Yeah.
And also, just to break away from the 4 conditions we had in mind too, I think this is going to be I find this one fascinating. But there's another disease called Huntington's disease, which is a genetic one. It's not the same as Parkinson's, but it does affect a similar area of the brain. So it affects that basal ganglia and substantia nigra, and the dopaminergic neurons. But instead of causing them to not produce as much dopamine, it ends up, at least in the early stages, with an overproduction. And so instead of having freezing, they almost have the opposite of like uncontrollable writhing movements, which we call chorea. And so they end up with this constant flow. And it's obviously quite debilitating in a different way, where instead of being stuck, they're fighting these uncontrollable movements that are against their voluntary will. And so it's an example of a specific area that can be affected by 2 diseases in 2 very distinct ways, which I think is quite an interesting example.
Yeah. One more thing I think is going to be important to mention as well is that with the reduction of dopamine producing cells, meaning less dopamine, there can also be behavioral changes that come with that as well.
Absolutely.
And so, because again, dopamine is a huge part in motivation. So a good way to think about this, which we might touch on a little bit more later, is the medications for Parkinson's that essentially look to try and give artificial dopamine. And so, like in Huntington, sometimes with the medications we can overload on too much dopamine, and so sometimes we'll have some behavioral changes timed around their medication when they're more on the higher side of dopamine circulating within them. They can get a little bit more, a bit more.
It looks a bit like Huntington sometimes.
Yeah.
Uncontrollable movements. Yeah.
And then on the other side of it, when medication wears off, they can have almost a noticeable change in their presentation and just how they maintain their themselves in daily life.
Yeah, I know it's can be quite. One thing I find quite interesting to work with Parkinson's clients is as that timing of medication can really affect their mood as well. Even though just dopamine is not responsible for happiness, it does have an influence on that motivation feeling and mood. And so I've sometimes seen that when people are in that kind of under-medicated state and feeling like they're a bit stuck because they're getting all those freezing symptoms, at the same time, they'll also have a bit of a low mood state and to feel a bit unmotivated to do things. So they end up with a vicious cycle of, I'm not feeling very good, mood goes down a bit, I don't really want to do anything, especially because it's hard to move, and then that makes the mood worse instead of a spiral. Whereas on the contrary, when they're on a hyper-medicated state and they're in that writhing state, they kind of really want to get out there and do something, they end up not thinking through movements too much, and so it can be a bit of a risk safety-wise. So almost like a little bit of mania. And I've seen people say they have balance impairments, but they're in this heightened medicated state, want to go do stuff, go, end up having a fall and an injury, in this hypermedicated state. So it's good to be aware of what state am I in. There are neurochemicals at play here. I need to be aware that it's affecting my mood as well. I think it's a really important education piece.
Yeah.
That leads in pretty nicely then to the next condition we want to talk about, which is multiple sclerosis or MS. This one, rather than affecting a very specific part of the brain, it affects the entire central nervous system. So brain down to the bottom of the spinal cord. But importantly, it affects things in a very different way than, say, Alzheimer's or Parkinson's disease. It's not a single cell type being affected, and it's not sort of associated with any protein tangles or anything like that. What it affects, it does something called demyelination. And so what is demyelination? It's, if you think of a cell, it's kind of like a long string-like cell. And so it receives information and propagates that along the cell, kind of like a wire, to the other end and then talk to another neuron. And like along a wire, it's wrapped in an insulation layer, like the rubber on a wire, to make sure that signal gets through nice and clear. And that's called myelin. And so what happens in multiple sclerosis, it's an inflammatory autoimmune disease where the immune system is attacking its own body. In this case, specifically, it's attacking the myelin of nerves in the central nervous system. And so you can imagine if the part of the brain has developed a signal that it's trying to send out, whether that's like a thought or a intention to move, if that signal is not going to get propagated along the nerve length as well as it should, it's going to get disrupted, and that's going to either change the signal, modify it, or cause it to not make it all the way down the spinal cord in the case of that region. And so it can manifest symptoms in a lot of different parts of the body in a different way depending on the region affected in the brain. It's a lot like the brain injuries we were talking about in the previous episode that are very location-based. If you get a lesion from MS, so that's an area of damage from the demyelination in this case, that's say in the around the hippocampus, then you might get memory impairments, kind of like Alzheimer's. If it's happening in the motor cortex of the frontal lobe, then you're going to have trouble initiating voluntary movement, have some weakness. Similarly, if you're getting a big lesion in the spinal cord, and that's where the motor signals are being transferred, you're going to get weakness again, but from a different part of the body. And also same with sensory. So you might have sensory processing problems from it happening in the parietal lobe, or you might have sensory pathway getting blocked in the spinal cord, ending up with numbness. So it can really depend. The key distinction from brain injuries being that it's a gradual build-up of this demyelination over time, as you see symptoms progressively get worse.
As well as coming back to multiple sclerosis, the name, many scars. The demyelination plus the formation of, the essentially scar tissue that progressively changes over time. Certainly not comparing it to Alzheimer's, but in the way of like the diffuse changes over time.
Starts to spread throughout a bit more.
Yeah, it starts to spread over time, which is where we start to get different symptoms popping up over the years.
Exactly. And I will probably touch on this again in a second, but these neurodegenerative diseases can have different speeds as well. And so in the majority of MS diagnoses are what we call this relapsing remitting form of multiple sclerosis, where symptoms can sort of spike up, which is like a relapse, they call it, and then they'll die off and you sort of come back to baseline. And sometimes baseline might not be quite back to where it was, but they do remit quite a bit. Over time, in some people, this shifts into a progressive form, or some people are diagnosed with a progressive form from the beginning, which is primary and secondary progressive MS. And in that stage, there's sort of progressive inflammation, progressive demyelination more rapidly over time. And you get these worsening symptoms and spreading throughout the central nervous system. Big key difference, though, from the next disease I'll mention is that it is strictly happening in the central nervous system. So the brain and the spinal cord, where signals are being generated or processed and then sent down the superhighway of the spinal cord to the body.
Next, which is called Charcot-Marie-Tooth disease. Now, I'm going to shorten it to CMT for the rest of this video.
Bit of a mouthful.
It is a mouthful, and I want to try and make this flow relatively smoothly, because trying to split up the difference between the central nervous system and the peripheral nervous system can be quite tricky. So the central nervous system is anything that runs from the head to the base of the spine. The peripheral nervous system runs from anywhere from the central nervous system out all the way to the rest of the body, all coming down our hands and fingers which is up here, and then our lower body, which is all down here towards our legs and feet. So CMT specifically impacts the forearms, but more typically the legs. Usually, the further away from the trunk of the body is what gets impacted the most. So think feet and hands. Now, CMT is something that has genetically caused. So it's present typically from when someone is a child throughout the whole lifespan. So these changes slowly happen, and as we get older, typically we see symptoms start to get a little bit more pronounced. Now, the changes that happen are slightly similar to what MS is in terms of they have the process of demyelination. They also have a loss of axons and like axon or degeneration.
Axon being that part of the nerve that's the wire underneath the myelin.
Yeah. So we almost have that double effect of losing that insulator sheath that runs the whole way along the nerves to improve that electrical impulse conduction.
Yeah.
While also losing the actual wire in the sheath, so that there's a slow weakening of those nerve impulses the further that you get away from the spine towards the legs, feet, hands, and arms. So typically in CMT, the feet is the first thing that can get affected. So a good way to think about this is, a symptom we can use to explain it is called foot drop. So imagine that this is the foot. I'll do my best to give you a little foot. This is the ground underneath. This movement of if this is the heel and this is the front of the foot, this is kind of lifting up of the foot. This muscle that does this can start to have, like we said, a reduced amount of electrical impulses going to it, which therefore reduces its strength. So this muscle actually helps to protect our foot posture. So typically someone with CMT can have a really high arch, so they the rise of their foot comes up a lot higher. So it's actually called pes cavus, but we won't go into that too much today. So they end up with a bit more of a foot deformity of a really high arch and not being able to lift their foot up as high, which again can contribute to trips, falls, struggle with gaining speed, slowing down, changing direction, and is a big risk factor for falls.
If someone's listening to this, I think a burning question they may have is, say they have multiple sclerosis, and they've listened to that, and think, hey, I have foot drop as well. Does that mean it's also the exact same thing that's happening as in CMT?
No, because CMT is specifically happening to the nerves that are further away from the central nervous system. Whereas someone with MS can absolutely have those symptoms, but it can be more coming from the central nervous system, losing myelin, or from where the brain is actually impacted. So same symptom, different causes.
Yeah, I think it's one of those important things where the underlying pathology can be quite important. Another factor that can differentiate different mechanisms and different regions is speed. And so all of these conditions have in common is that they progress over time, but they can differ in speed. And so we might just rattle through a few examples of that being the case. Coming back to, say, Parkinson's disease, it's disease affecting those dopaminergic neurons in the substantia nigra. Another similar condition that affects those areas in the same way is multiple system atrophy. So it's another Parkinsonian disease, they call it, but it's a lot more aggressive. And so
it's in the basal ganglia,
the basal ganglia
as well,
yes.
I believe. Yes.
Yeah. So that whole deep region of the brain that can present with similar symptoms of Parkinson's initially, but it's a lot quicker in its action, and so it can progress. Typically, life expectancy after diagnosis can be somewhere between 6 to 10 years, which is a lot shorter than Parkinson's disease. And I mentioned earlier that multiple sclerosis has also those different forms that can change speed over time.
Yeah. Hey everyone, just quickly, could you please double check you've hit that subscribe button? Because it is the best way of supporting the show.
And if you're watching on YouTube, don't forget to hit that bell icon as well, so YouTube will notify you when we have our new episodes out every week.